Hi, so we're back and we will resume our discussion of dimensionless numbers in fluid dynamics. We went through a quick survey of several of these when we met last, and today what we will do now is special attention just to the Reynolds number. For two reasons. You will see we will encounter something called dynamic similarity, which will illustrate the special importance of the Reynolds number. That's one thing. Secondly, the Reynolds number is something that's the Reynolds number and the magnetic Reynolds number, which we will not discuss today. These two are things that are especially important in astrophysics, and so hence my motivation in doing this. So we will do the Reynolds number, and we will try to understand what dynamic similarity is all about. And in the same breath, having discussed dynamic similarity, we will also revisit the problem of lift on an aircraft wing that we discussed briefly some time ago. It's just a very interesting application of the dynamic similarity idea, and we will revisit problem of lift. Specifically, we will outline a simple treatment of what's called the Kutta-Joukowski theorem. Okay, so without further ado, let's launch right into it. So we're talking about dynamic similarity, dimensionless numbers. We have already talked about this a little bit earlier. Dimensionless numbers. We have not yet talked about dynamic similarity. We'll do that. Specifically, we'll focus on the Reynolds number, albeit with a slightly different focus. And like I said, we will also talk about the Kutta-Joukowski theorem and aerodynamic lift. Right. So we will start with the now familiar Navier-Stokes equation. What we were doing yesterday. Now remember this entire thing. This is essentially Ma, and these are the different components of F. This is the F due to the pressure gradient. This is the F due to body forces. And this is essentially the viscous term. Right? Yes. And if you remember the last time we did this, we were not writing it in this form. We were writing this entire thing in the Lagrangian form. We were simply saying like that. Times rho, of course. We were multiplying this whole thing by rho. That's what we were doing. In this case, we've written it out in Eulerian form, and it should not be a big deal for you. You should be able to switch between one form and the other. Right. So now, having written it this way, we will now specialize to there's an advantage in writing it this way. We can specialize to steady state situations, which is to say the partial d partial t is equal to 0. In other words, for an observer who is in the lab frame, okay, he or she does not see any explicit time dependence. And the other thing is we will neglect body forces. We will neglect body forces. We won't bother about, just for simplicity. Okay, having done that, so we are only left with, so what are the terms we are left with? We are left with this, we are left with this, and we are left with this. And so that's what this equation is all about, right? Again, this is really just an F equals ma equation, just a slightly specialized version of the Navier-Stokes equation, right? Okay, so now this is a very important step. This marks a slight departure. I mean, it all boils down to the same thing at the end of the day, but the philosophy is important, and it marks a slight departure from the way we were doing things. This has to do with our discussion of characteristic. Remember when we were talking about Reynolds numbers yesterday, we were defining Re as V times L over nu. I beg your pardon for the slight change in notation from now on. Today, when we were discussing, we will be replacing this capital V by capital U. Okay, so this is something that you need to keep in mind. And so when we discuss, Reynolds number during the last session, this is of course the coefficient of viscosity, but the V was some characteristic velocity and the L was some characteristic length, right? Here what we are saying here is that if the viscous, we consider a situation where the viscosity is not, probably this is the better way to put it, at the back of our minds we really should be thinking about a situation where the viscous term is only a perturbation. It's not the overwhelming, it's not the dominant term in the equation. Okay. In other words, yeah, so this term is only a kind of a perturbation. Think of a situation where you have say water, moderately viscous fluid like low viscosity fluid like water flowing around a sphere. So you can imagine that, you know, there any kind of sticking or anything viscous effects, in other words, happens only on the boundary, on the surface of the sphere, or the solid sphere. Far away, the water flow is pretty much undisturbed, isn't it? Far away from the surface, the water flow is pretty much undisturbed, and water continues to flow as it were, as though the sphere was not at all there. And it's that velocity where viscous forces or viscous effects are not important, say far away from the boundary. That is the kind of velocity we're talking about here as u. Okay. So it makes sense to think of the velocity in units. In other words, whatever velocity you see here, the small u, we normalize this with respect to a capital U, where the capital U is the velocity, is sort of the undisturbed speed. Okay. If you want to think of a concrete situation, you can imagine this, where you have a low viscosity fluid flowing past a sphere, and this capital U would be the speed of the fluid far away from the boundary of the sphere, sufficiently far away. Okay. Right. If that's the case, in other words, what I'm saying is I'm going to divide of course, divide both sides of the equation, so the equation itself is undisturbed, right? So I'm going to divide all velocities by u. In other words, I'm going to consider velocities in units of this undisturbed speed u. Well, if that's the case, then I can also consider pressure in units of rho u squared. You can verify that this has the units of pressure. Okay, so wherever I see p, I divide by rho u squared. And lengths in units of some macroscopic, this is the same concept we talked about, in some macroscopic length L. Okay. For instance, if you're thinking about flow past a sphere of diameter, say 1 centimeter, the macroscopic length would be say 1 centimeter or 5 centimeters, certainly not 1 meter, or certainly not 1 millimeter. Right. So this is the spirit in which we define the macroscopic length L. Okay. In other words, we introduce these dimensionless variables. X prime is x divided by L. Okay. U prime is u divided by this capital U, this undisturbed speed. P prime is, well, not quite p over rho u squared as this might have suggested, but p minus some pressure at infinity. Infinity meaning when you're sufficiently far away from the body, divided by rho u squared. Okay. So we're going to rewrite this entire equation in terms of these these prime variables, which are dimensionless. You can check that these are dimensionless, right? X and L both have units of say meter or centimeter, as the case might be. So x prime itself is dimensionless. Same with u prime. U prime is dimensionless. P prime is dimensionless. Okay. So this is dimensionless length. Okay, I mean, it's a bit of an oxymoron talking about dimensionless length, but length, it is length, it denotes length, but it does not have the dimensions of length. Okay, similarly, dimensionless velocity, dimensionless pressure. As elegant as these things might be, we were really doing this for a certain purpose. We will see but you have to be very, very careful while dealing with dimensionless numbers, because there won't be any warning bells that go off if you make a mistake. Okay, many times in an equation like this, if you're missing a factor of rho, if you're missing a factor of u or whatever, you just look at the dimensions and you can figure it out. Oh, there's something wrong here and I need to set it right. When you're working with dimensionless numbers, there won't be any such warning bells. Okay, so you've got to be really, really careful about your algebra. So if I'm going to introduce these dimensionless numbers, all of these, then, and I urge you to do this yourself, then the steady state equation of motion, which is just this, okay. The steady state equation of motion, again I reproduce this here, can be written as that, okay. And I urge you strongly to show this, okay, where the definitions of u prime, right, x prime, which does not explicitly appear here, and pre prime and everything are okay. There really should be a prime here. There should be a prime. In other words, this is actually p prime. Okay, they are given as, these are the definitions. And what does this delta prime mean? The delta prime simply means and so forth, okay, d over dx prime, d over dy prime, so on and so forth, okay. That's what this delta prime means, okay. And I would like you to you know, to show this, to show how this comes from this. It's fairly simple algebra, but it's important, okay. Now the thing is, when you derive this from here, there are some terms that are left over, and all of those are bundled together in this term. And you guessed it, here is where the Reynolds number Re makes an appearance, where Re is equal to, and here I am using the mu that we were always working with, the kind of viscosity coefficient that we were always working with before, but it's really the same as this, because mu is nothing but rho times that, okay, where this is what it is, okay. So it's the same definition that we had done earlier. So it's essentially the ratio of terms that we discussed the last time we met. Exactly the same definition, but this is how it comes about. It comes about in a slightly different way. I urge you to think about this in both different ways and familiarize yourself, make yourself comfortable, because the reason I say this is because this version of the momentum equation, or this version of the Navier-Stokes equation, will lead naturally to an understanding of the concept of dynamic similarity, okay, right. So the Re is the dimensionless. You can verify that this is indeed dimensionless. Nu has the dimensions of centimeter per second times centimeter, in other words centimeter square per second, and therefore the Reynolds number is dimensionless. And as we discussed the last time we met, the Reynolds number gives the ratio of the inertial forces to the viscous forces. Okay, this is how we did it. I mean, this particular statement is how we did it the last time we met. Today, we're simply saying that when you non-dimensionalize this equation using the prime variables, there are some terms left over which can be neatly bundled together into the Reynolds number. Okay, two ways of looking at the same thing, and both ways are important to understand. Okay, so let's go forward. Right. So this is one thing. This is about the momentum equation itself. Let us now go back to an equation, the vorticity equation that we discussed earlier. I'm saying this just because, just to make you comfortable with the fact that this non-dimensionalizing given by this kind of non-dimensionalizing is useful in different situations. Okay. So remember, the vorticity equation was essentially a dynamic equation for u. Okay, you specify the u at a given time, and this gives the evolution, strictly speaking, of omega, which is essentially omega which is the curl of u. If you recall, we remarked that this is a completely fully specified dynamical equation for the evolution of omega. Sure enough, there's a u there, but the u is the uncurl of omega, right? Now, so this was for inviscid fluids where viscosity was not important, and with viscosity included, this becomes, and I would urge you very strongly to show this, to show that the vorticity equation with viscosity included becomes this. So, in other words, you have this this additional term here. Why am I talking about the vorticity equation? Because it's a dynamical equation for u, just like the momentum equation is. Okay, it's just a slightly different way of looking at things. And there are some advantages to non-dimensionalizing the vorticity equation also, which is what we are going to do now, right. So, at any rate, with viscosity included, you have this additional term, which of course completely alters the character of the equation. Here you only had first derivatives, right. Curl is just, it just involves d over dx and so on and so forth. Whereas here viscosity, you have this has a Laplacian included. So, you have d square x over dx square and things like this, right. Not very surprising, because you remember even in the Navier-Stokes equation, the viscosity, whenever you have the viscosity included, it involves second derivatives, and that changes the character of the equation. If you just had these two terms, this would be the steady state Euler equation, in other words an equation that applies to inviscid, strictly speaking inviscid situations. But when viscosity is included, you have this term and you have the appearance of second derivatives, and so the same thing here too. Okay. Second derivatives, except there is a vector Laplacian now acting on the vorticity, right. So, here is another interesting thing. We remarked earlier that this quantity called circulation, which is defined as right, this is perfectly conserved for an inviscid situation. I would like you to think about whether the circulation will be conserved in this situation now. Okay, the answer, I will tell you the answer is no. Okay, circulation is not conserved when viscosity is included. Circulation can be created or destroyed. Okay, and we also talked about situations such as aiming a hose of water at a wall. Okay, a perfectly laminar flow of water, but when it hits the wall, you will see that the laminarity of the flow is destroyed and vortices start appearing. And why is that so? It seemed like there was viscous effects were not important in the bulk flow of the water up until it hit the wall, but suddenly viscous forces seem to be, circulation seems to be generated when the jet of water is hitting the wall. So why is that so? Okay. The brief answer is that yes, viscosity is not important in the bulk of the flow, but just when the jet of water hits the wall, it comes to a crashing halt, and therefore either the vorticity or the velocity, depending upon how you look at it, has a large jump. Okay, so the first derivative is quite large, and second derivative is even larger. So therefore, even though nu might be small, it's being multiplied by a larger quantity, and therefore viscous effects become important in the boundary region where the jet of water hits the plate or the wall, and when viscous effects become important, circulation need not be conserved, and a situation where there are no vortices or no vorticity in the flow need not remain the same, and it's everyday experience that we see lots of, we see the generation of vorticity just where the jet of water hits the wall, right. This is an everyday experience. Okay. Right. So, in order to answer this question, you can follow the very same arguments leading up to Kelvin's vorticity theorem, which we discussed earlier. Just a bit of an aside, interesting aside, right. So, now we try to non-dimensionalize this equation. Okay, non-dimensionalizing u is fine. We just introduce a u prime. In other words, we divide it by the large scale u, the undisturbed u. But how about omega? Well, that's not, omega is non-dimensionalized. Well, x prime is again, non-dimensionalized in the same way. Omega is non-dimensionalized this way. Okay, so you have a L over u appearing. Okay, why is that? I urge you to think about this also. I urge you to think about the appearance of this term. It's just dimensional. Okay, you will find that L over U has the dimensions of, well, I urge you to think about this. What are the dimensions of L over U? What are the dimensions of omega? And what are the dimensions of L over U? The dimensions of omega are easy enough to figure out. Omega is simply the curl of U. So, whatever the dimensions of U are, say centimeter per second, you divide it by centimeter, right? Because this is, the dimensions of this are something like, right? So, it is 1 over centimeter, right? So, if you figure this, if you understand this, you'll quickly understand why we are introducing this kind of a factor L over U while non-dimensionalizing omega. So, with this we can rewrite the vorticity equation as like that, and no surprise, again I urge you strongly to show this. Okay. So, with these non-dimensionalized variables, the vorticity equation is written like so, and as before we have the appearance of this term 1 over Re, where the Reynolds number as before is simply UL over nu, the same thing, right. Compare this with the original equation, that, right, it looks exactly like the same with everything, yeah, so I have not told you what the T prime is, I leave that to you. I will say what is T prime? I leave you to think about that. Again, so what is time non-dimensionalized? What's the unit like? Just like here, this is in order to non-dimensionalize the vorticity, I use L over U. So what should I be using to non-dimensionalize T? It's not a difficult answer. It's some combination of U and L, right? So having non-dimensionalized this, it looks exactly like this, right? With primes on everything, primes even on the nablas, right, on the deltas, right, except for the appearance of this 1 over Re in the non-dimensionalized equation, right. So it's very similar to the way in which we did the Navier-Stokes equation, and right. So the advantage in doing this is that this is the concept of dynamic similarity which I alluded to. Flows around different geometrically similar objects can be computed using the same equation, this or the non-dimensionalized Navier-Stokes equation, as long as the Reynolds numbers are the same. In other words, yeah, so we will talk about this in a minute. Okay. So I want you to remember this particular phrase, geometrically similar objects. Okay. In other words, a small copy of a larger object, say you have an aeroplane wing or a ship or whatever, okay, as long as I have a miniature model of that large ship, miniature model meaning a model that's in every aspect exactly similar to the larger ship, except that it's all shrunken in size, okay, or larger as the case might be, but geometrically it's exactly the same as my original object. Okay, I can investigate the dynamics of the flow equally well in both situations, on the original object or on the miniature object, as long as the Reynolds number in the two situations are the same. This is the advantage in using a non-dimensional equation like so. Okay. So one can make a small geometrically similar model of a large body and perform experiments on it. Say, for instance, why would I perform an experiment on it? For instance, to find the drag, to find the aerodynamic drag. This is a very practical application. You have an airplane moving through the air, and as an aerodynamic aeronautical engineer, if you were to try to figure out the fuel efficiency or so for even a car, for instance, you are very interested in the drag, right? That's experienced by the car, but you don't want to take the entire car into a wind tunnel unless you're very sure of things and you're ready to invest that kind of money. Instead, you would prefer to perform experiments on a miniature model of the car or a miniature model of the airplane, okay? And the results are guaranteed to be the same as long as the Reynolds number in the two situations are the same. Okay, so I want you to think about this carefully, and this is at the heart of this concept called dynamic similarity. And one instance why one would want to perform such an experiment is to, for instance, find out the drag. I want to minimize the drag, obviously, to maximize the fuel efficiency or many other things, right? So here's an example of geometrically similar objects. This is a miniature version, right? It's a miniature version of the ship, right? So the L1 is smaller than the L, so on and so forth. So I mean, I have the ship, and I want to find out the dynamics of the ship, how fast it can move in water under certain conditions, so on and so forth. What's the drag? Many other things. But I cannot afford to build the entire ship and then do experiments on it. I would like a fair idea of things before I actually design the ship. I want to optimize the design. So I build a miniature version, take it to maybe an artificial tank or something like that, and perform experiments on it. But I can do this, and I'm guaranteed relatively accurate results only as long as I'm guaranteed that the Reynolds numbers are the same in the two situations. And so much of this work is due to Osborne Reynolds. I thought it's always interesting to think. I urge you to do a Google search on Osborne Reynolds to see the wide variety of his interests. For us, I mean, we are only interested in the Reynolds number, but people like this have done a wide variety of things. So it's an interesting aside. Having said that, so before we conclude this particular part, I just want to emphasize one thing. We kept saying that the Reynolds numbers in the two situations, situation 2 and situation 1, the Reynolds number in these two situations has to be the same. Now remember, what is the definition of the Reynolds number? The Reynolds number is, right? So the U here is different from the U here. The L here is different from the L here, right? This is a miniature version, so the characteristic length is obviously different from the characteristic length for the bigger version, right? So what does it, but I want to insist that the RE has to be the same in both the situations. Okay, so what does this mandate? Can I perform experiments? Suppose I was interested in the dynamics of water, say seawater for instance, on the large scale ship. Can I have the very same material? Can I have the same seawater in this experiment that I'm doing with the miniature object? The answer is no, because both the U and the L in this situation are different from the U and the L in this situation. And if I have to keep the ratio constant, I have to change the nu, right? So the RE has to be the same. In situation 2 and situation 1. But that means that I have to perform my experiment with a different fluid in this situation as opposed to this situation. I have to think carefully about exactly what that fluid should be. Only then I am guaranteed that the RE will be the same. Okay, so with that we will end this segment. Thank you.